Okay, this lesson is called Intro to Linear Programming. Now, this first definition is linear programming, not a surprise. Okay, linear programming is a technique that identifies the minimum or maximum value of some quantity. The quantity is modeled with what's called an objective function. Limits on the variables in the objective function are called constraints, and they're written as linear inequalities. We'll talk about this more on the next page when we get to the actual examples. The feasible region contains all the points that satisfy the constraints and the maximum value and the minimum value. The maximum value and the minimum value of the related function always occurs at a vertex of the feasible region. Okay? So there's two types of problems we could do. We could have bounded problems and unbounded problems. Okay, so for the bounded problem, okay, first of all, this thing that's shaded, that's called the feasible region. This is a vertex, that's a vertex, that's a vertex. And again, this shaded region, that's called the feasible region, okay? So this one on the left, that's called a bounded feasible region, bounded, because the feasible region is enclosed, okay? The maximum value and the minimum value always occur at a vertex for the bounded, okay? For the unbounded, the feasible region is open and it can go on forever. And these have either a maximum or a minimum value, but not both. And again, that always occurs at a vertex. Okay, so I have 4 examples today. Here's example 1. Graph the system of constraints. Okay. Now, these are the constraints, the inequalities. These are called the constraints. Okay. Hold on a second. Okay. So again, these are called the constraints, and this is called the objective function. This is what we want to either maximize or minimize. Okay. So first thing we're going to do is we're going to graph the constraints. Okay. This first one has a y-intercept of 5 and a slope of -1/2. Y-intercept of 5, slope of -1/2 means go down 1, right 2, down 1, right 2, down 1, right 2, down 1, right 2, down 1, right 2. Let me graph that. Okay, now we have to shade that. Let me get my pencil. We have to shade that. So, if you remember, if your inequality is in y equals mx plus b form, and it's less than or less than or equal to, it means shade below. If it's greater than or greater than or equal to, it means shade above. Okay, so this one is shade below. X is greater than or equal to 0 and y is greater than or equal to 0 means you're in the first quadrant of the coordinate plane. Okay, so we're shading below this line and we're staying in the first quadrant of the coordinate plane. So this is my feasible region right here, the thing that's being shaded. That is my feasible region. Let me get another color for the vertices. So I'm going to color the vertices of my feasible region in blue. So this is a vertice, that's a vertex of my feasible region, that's a vertex of my feasible region, and that's a vertex of my feasible region. Okay. The question asked you to state the vertices of the feasible region. So let's go ahead, let's do that above. The vertices of the feasible region are, 0, 0, 10, 0, and 0, 5. 0, 0, we have 10, 0, and then we have 0, 5. So now what we're going to do is we are going to test each vertex with the objective function. Let's start with vertex 0, 0. I always like to copy the objective function. So this is the objective function. C equals negative 8x plus 11y. Now what I'm going to do is I'm going to replace the x with 0 and replace the y with 0. And let's see what we get. 0 plus 0 is 0. Now let's do the same thing with our next vertex. Our next vertex will be 10, 0. Copy down the objective function. This time replace the x with 10 and the y with 0. And that gives you C equals negative 80. Now let's test our last vertex, which is 0, 5. Replace the x with 0 and replace the y with 5. And that gives you 55. Now, if you look at the three numbers we got, negative 80 was the smallest number, so that's going to be our minimum. And we got 0. 55 was the biggest one, so 55 is going to be my maximum. But I want you to write the answer a certain way. I want you to say the minimum value is negative 80. The minimum value is negative 80. And it occurs at 10, 0. Then I want you to say the maximum value is 55. And it occurs at 0, 5. Okay? Let's do another one. I'll graph this one a little faster because it's just like the one we just did. Our top inequality has a y-intercept of 6 and the slope of negative 3. So you can go down 3, right 1. Down 3, right 1. Down 3, right 1. Graph that. Connect those points. Since it's in y equals mx plus b form, and it's less than, it means you're going to shade below that line. And our other two constraints means we're going to stay in the first quadrant. So your feasible region is going to be this. That's your feasible region right there. Let me label the vertices of the feasible region. We got 0, 6. We got 2, 0. And we got 0, 0. So our vertices, it wants us to state the vertices. I'll do that up here. The vertices are 0, 0, 2, 0, and 0, 6. Now let's test each vertex in our objective function of p equals x minus y. Let's start with vertex 0, 0. Again, I like to just copy down the objective function under that. P equals x minus y. So p equals 0 minus 0. So p equals 0. Our next vertex is 2, 0. So again, you can do some of this a little faster than I'm doing it. I'm just going slow. The objective function p equals x minus y. So p equals 2 minus 0. So p equals 2. And the next vertex is 0, 6. The objective function, p equals x minus y. P equals 0 minus 6. And that gives you p equals negative 6. So let's look at our three answers that we got. Negative 6 is actually the smallest one, so that's the minimum. And 2 is actually our largest one, so that's the maximum. So then let's put that in a sentence. The minimum value is negative 6, and it occurs at 0, 6. And the maximum value is 2, and it occurs at 2, 0. Okay. Next example. A little more difficult. We have 4 constraints. X is greater than or equal to 0. Well, that's a vertical line at 0, shade to the right. Y is greater than or equal to 1. That's a horizontal line at 1 and shade above that. Our next, so that's y equals 1. You're going to shade above that. 5x plus 10y is less than or equal to 40. That has an x-intercept of 8. Remember, x and y intercepts. And a y-intercept of 4. X-intercept of 8. Y-intercept of 4. Connect those. Okay. Hold on 1 second. Just bear with me 1 second while I draw that. There we go. Got it. And our last line has a y-intercept of 7 and a slope of negative 2. So down 2, right 1, down 2, right 1, down 2, right 1. So now when you do your shading, do like we've done previously. You can either pick a test point or use the shortcuts depending on the method. But when you shade it, this is going to be your feasible region right here. This one has 4 vertices. We got 1, we got 0, 1, we got 0, 4, we got 2, 3, we got 3, 1. So 4 vertices. Let me just label those above. So our vertices, we had 0, 1, we had 0, 4, we had 2, 3, and we had 3, 1. So I'll go a little faster this time because we've done a bunch already. But let's start with vertex 0, 1. Our vertex function is p equals 25x plus 30y. So p equals 25 times 0 plus 30 times 1. That gives you 30. Next, vertex 0, 4. P equals 25x plus 30y. 25 times 0 plus 30 times 4 gives you 120. Next, let's do vertex 2, 3. P equals 25x plus 30y. P equals 25 times 2 plus 30 times 3. So 50 plus 90 equals 140. And our last vertex is vertex 3, 1. P equals 25x plus 30y. So 25 times 3 plus 30 times 1. So 75 plus 30 is 105. So we got 30 is our minimum. That's our smallest number. And 140 was our maximum, our biggest number. Let's put those in 2 sentences, and then we'll move on to the last problem. The minimum is 30, and it occurs at 0, 1. The minimum value is 30, and it occurs at 0, 1. 30, and it occurs at 0, 1. The maximum value is 140, and it occurs at 2, 3. Okay, we have one more problem to do. Those first 3 examples all had a bounded feasible region. This last problem has an unbounded feasible region. So let's see what that looks like. Okay, I'm going to go a little fast through the graph because we've done a lot of this already. But our first line has a x-intercept of -1 and a y-intercept of -2. Okay. Our next line has a y-intercept of 7 and a slope of -2. So down 2, right 1, down 2, right 1, down 2, right 1. Those 2 lines, I believe, are actually parallel. And our last line has a slope of 1 and a y-intercept of 4. Okay. I'll go quickly through the shading, but because we've done it a lot already. But this is going to be our feasible region right here. Unbounded. Unbounded, which means we have a minimum or a maximum. This one's going to have a maximum. Okay. Our vertices are -2, 2, and 1, 5. The feasible region is unbounded. It appears that there is no minimum value. So what we're going to do is we're going to test each vertex. Let's test vertex -2, 2 in our objective function of a equals 4x plus 2y. So 4 times -2 plus 2 times 2 will give you -8 plus 4 is -4. Now for vertex 1, 5. Objective function a equals 4x plus 2y. A equals 4 times 1. Plus 2 times 5 gives you A equals 14, which is our maximum value, and there is no minimum value. There is no minimum value. So I'm going to say the maximum value is 14, and it occurs at 1, 5. There is no minimum value. All right. So that is the end of that lesson. That lesson was called Intro to Linear Programming.